topic is titled Overview of Quantum Cryptanalysis of Lattice Systems. But what I'm actually going to say is about cryptanalysis or hardness of SVP. So we've just heard that all cryptographically interesting problems like CIS and LWE, they are, so if you can break those, you can solve some hard problems in lattices, and the next relevant question would be how hard this problem actually are, right? And it also works another way around, because the way we usually attack LWE and CIS, we actually solve the shortest sector problem. So it's both ways, and in both ways, it's interesting to actually see how hard this problem is. This is an outline of my talk. I'm going to very briefly again introduce the shortest sector problem, although you've just heard it. And then I'm going to focus most of my time on the quantum sieve. The reason I'm doing it because there are like lots of these constants floating around the previous workshops, and I just want to make them maybe a bit more understandable. And also I should emphasize that I'm going to keep everything asymptotical. I'm not going to go into details about prefactors, but if you want to do this, you should start from something, and this perhaps it will be just a start. Okay, so at least you can fix the exponential and the polynomials you could try to draw from the algorithms. All right, so this is my slide about lattices. A lattice is a finitely generated discrete subgroup in Rn, additive. And the invariant we're going to be interested in is, I keep the same notation as in the previous talk, so lambda 1 will be the minimal length of the non-zero vector in the lattice. And the good thing about this one is that we know approximately what it is. So there is a Minkowski bound that tells us what this quantity is about, and it's, for lattices we care about its tight. For algorithm, that means that we know when to stop when we found something. So there are basically two ways to target this problem, two families of algorithms. The one is called enumeration. I will briefly say about this at the end of my talk. And the second one is sieving. Two crucial differences between them is that the first one is exponential. Super exponential, it's 2 to the n log n with polynomial memory, and the polynomial memory keeps the same also in quantum version, where the quantum version of enumeration shaves off a factor of 2 in the exponent. So actually, if you can improve the constant in exponent in a classical regime, you could also improve that in the quantum regime by factor. For sieving, these are the mysterious constants. The mysterious constants are the 292 for time, classical time, and the 265 for quantum time. And the purpose of my talk is actually explain the nature of these two constants. All right. And I should also say that I'm going to be focused on heuristic sieving. I think there was a work done on provable sieving algorithms, but the constants are far bigger than 1. For classical time and for quantum, I think they're around 1. So, okay, what is sieving? I'm going to describe the very basic sieving, which is called GUI Vedic Safe, but it's not the first algorithm that introduced sieving. The first was GUI-AKS. And I'm going to do the simple version of GUI, what's called now GUI Vedic Safe. So the main idea is the following. You have a basis. You're given a lattice by a basis, so it's a compact representation. And you start sampling Gaussian vectors from the lattice. And you can do that efficiently as soon as you're not targeting very short vectors immediately. So you can draw Gaussian long vectors in polynomial time, in polynomial dimension. And you draw many of them, such many that they appear to live close to each other. And this closeness you want to find, you want to detect this closeness such that the difference becomes shorter. So basically on the picture, what I have is I sample orange vectors, I put them into a list, and I want to find pairs that give me something shorter. It looks like this. Once you find something shorter, you put them in a new list. And then you iterate the same process. Now, what you want to do in provable version is to actually control that you keep Gaussian distribution over the whole lists. But heuristically, you usually assume that whatever we put, it remains the distribution we want, although it may not necessarily be true. You keep this iterating this process by finding short paths, and after some, at most polynomial many steps, you actually find something short. So there are two questions that arise if you want to analyze this algorithm. Oh, sorry. I want to first make a quick reference to my previous talk, is that when I spoke about the k-list problem, this is an example of a two-list problem where your two lists lie on the sphere. Why on a sphere? Well, that's because once you sample Gaussians, they are always concentrated on the boundary, so on the surface. And without loss of generality, we can assume that what we sample actually lies on the unit sphere when we normalize. It may not necessarily be, of course, true because we are working with a lattice, and lattice points do not lie directly on the sphere. But if like at the beginning of the algorithm, when we sample long vectors, they will be approximately the same norm. And actually, from the runs, from the practical experiments, the lists, the vectors we experience during the runs of the algorithm, the norm doesn't differ by much. So the assumption that we always lie on a sphere is not a very strong assumption. So then there are two questions that arise if we want to analyze this algorithm. The first is, how large should we sample originally the vectors? How many vectors do we need? And the second is, of course, what is the time to find to solve this two-list problem? So to analyze this, to answer these two questions, what I want to introduce is a tool that we use to analyze it. There are various tools, but I'm going to present the one that I find most convenient and extendable. So we're going to look at distribution of gram matrices. So just to recall what a gram matrix is, if we have k vectors from a unit sphere, the gram matrix would be just a k times k symmetric positive definite matrix that contains the inner products. So you should think about k as being a small constant, for instance, 2, when we work with two vectors. I'll put k because later we will need k equals 3. So the C is a matrix that contains the inner products. It has one of the diagonals because we are from the unit sphere, and out of diagonals are inner products of xi, xj. So one thing to notice about why this is a useful notion, first of all, because it determines the two norm of, so imagine I want to sum the two vectors, x1, x2, and the sum of x1 plus x2 is determined by the gram matrix in the following form. If you just open the norm, you'll see that this will be, let's say, k is 2. It's 2 times twice the inner product x1, x2. Okay. Of course, you can extend it to k. Now, and the tool that I'm going to use is the distribution of these gram matrices. And the distribution is actually, we know how they're distributed. We know what distribution they follow. And in particular, that's what we used with Gottfried Herald in order to analyze a k-list version of that, is that if you draw a gram matrix, and I will explain in a second what I mean by that, is the probability to actually find this k vectors that follow this distribution, this inner product constraint, is very close to the determinant of this matrix to the power n-half. Think about k as being a constant, so it will be around n-half. And also the constant here, we also know, we actually have a precise formula for this density function. So this one we can approximate pretty well. So in other words, if you want to find, let's say k equals to two vectors whose inner product is what you fix, the probability that you find those on a sphere by random sampling is this one. What do I mean by drawing a distribution? By drawing a gram matrix? What I mean by that, let's say k equals 2, that means I just draw two Gaussians with uniform direction, and then I normalize. And that gives me the C. This is very closely related to what's called the Wishart distribution, except that the Wishart distribution it doesn't normalize. But this is a known distribution of k-dimensional Gaussian, of a joint distribution of k-dimensional Gaussians, and the joint, I mean the inner product of the side. And if you just look at what the density function for this distribution, you will actually recover this formula. So this is just the tool to use for the analysis of this sieving algorithms. How to use that one? Well, first, it answers the question how large the edge should be. So assume that at each step, we want to find two vectors that are close, that give me whose sum gives me 1. So that means I'm going to target the search for two vectors whose inner product is cosine of pi over 3, and the cosine of pi over 3 is 1/2. So this is the picture. So this is my x1, x2, and I'm going to target the distance 1 in this sum. So this is a triangle with degree 60 angles, pi over 3. So this one, the inner product between x1 and x2 is the cosine of pi over 3, it's 1/2. So if you plug that in, you will immediately recover the constant for the list sizes. And so one of the things to notice here is that because this probability density function is exponential in n, you will notice that all the others potential inner product configurations that also give you 1, they're exponentially smaller in probability. So it could happen that you could sample some other two vectors that give you 1 or something shorter, but they exponentially, the probability that they appear is exponentially smaller than that one. That's good. So you could put any inner product constraint inside and see how many points you need to target, not let's say 1, but 1/2, 1/3, or whatever, by just plugging into the So that is a way to compute the required list sizes. And if you do a naive search, so what do we do next? We find paths into lists of size that I've just shown. What do? You can do a brute force search over the paths. That would cost you the square of the list. And the square of the list is this exponent. And this is precisely what appeared in the paper of GUI Vedic. They had the memory of 2075 and this runtime. Okay, so this is how I achieve one magical exponent. The second exponent that improves this naive brute force actually uses a technique from the naive search. I'm going to show you these techniques and the way we can analyze them, both classically at the beginning and then quantumly. Okay, so what do we do? The technique is for that is called Encarta filtering. So there are things that called Encarta hashing that uses functions. Well, filtering do not use functions; they use more. So they do not use. So filtering is not about having functions, but rather having regions and pre-images of a function. So this technique is actually not only used for spheres, but also for codes. That was first appeared in the work of Mayozerov related to the decoding. So not for the angular metric or Euclidean metric, but for Hamming metric. And In the area of sieving, it's appeared in papers by Becker, Kagama, and Lachov in 2016. So the idea is as follows. You forget first about your lists at all, your data that you have. And you choose independent vectors, vectors on your sphere, which are called centers. So these centers, so you take a point on a sphere and define it as the center of a ball. And let's say the radius of this ball is alpha. You don't have to cover the whole sphere. There can be some empty holes. They can intersect. It doesn't matter much. And what you do next is, for all your points in the list, xi, you find all the centers. You find all the u's where the xi land. So for instance, if you target x3, if you process x3, you should put this into the center or the bucket that is defined by the center of u3 and u2. And you do this for all of them. This is what is called in the multi-sensitive technique an update phase. And the second phase is what's called the query phase. So there again, for all your vectors in the list, you're gonna ask, okay, please show me all the centers that lie within the radius beta, and with these centers, give me all the points I bucketed at the beginning. So for this point q, that will return me the center u3, and the center u3 contains x4 and x3. And then I check whether these two are short. Also, it will return me probably u4, and I'm going to check against x1, x6, and x10, x2. And I'm going to check whether I have something close. So without checking all of them, right? So I'm going to only focus on those that have higher chances to be close to my query point. So that's the whole purpose. All right. So how to analyze this algorithm? So the question is, okay, there are two questions actually. First, you may ask, how do I find centers? So I'm giving you a point either in the update phase or in the query phase. And the question is, how do I find the relevant points, the relevant centers, the relevant UIs that lie within the alpha radius to my x from the list. Now there are various, I don't think there are various techniques, but at least one that works is that you do not choose your UIs randomly on a sphere, but rather structured. And in particular, they should appear as that's the idea of in the Mayoserov and the BTGL16. They are coming from the product code. So the way you do is as follows. If you have an x, here, let's say n-dimensional vector, and the way to find the u, which comes from a product code, is the first. Okay, decode me first. The first, let's say small o of n, let's say square root n coordinates with respect to this code, and this code has length square root n. So that would, if it's a random code, it will cost you 2 to the square root n. Could be the first contribution to the small o term in the exponent. But it's not n. It's square root n. Let's say you've got all vectors from this code that are somewhat close to x1. Then you continue with x2 and then up until the t. This way you can sort of amortize the search for the close u by not taking them uniform random, but from the code, and you exploit the fact that they're from the code, and you have a decoding procedure. So that will that for example will cost you 2 to the square root n. Of course, you should also notice that it relies on the fact that we have a good spherical code in the dimension we want, or somewhat good. So the second thing to notice is that this is what was proved in the BTGLs, that the UIs are not uniform random anymore from the sphere, but they're close to being so if you choose the length of your spherical code large enough. So the length cannot be like a constant. That won't be uniform anymore. But some function of n will suffice, small of n, small o of n. So if we go to the analysis, so basically that what tells you is that we can find relevant vectors, all relevant centers to a given vector, in time proportional to the number of those that you want. Question number 2: what is the time to update? So recall that for each x, we were to find an element, a relevant center, that was at the target distance alpha from it. The time to do that is the number of all relevant vectors you are going to find. And this time is given to you by the total size of the relevant centers times the probability that ui and x are a distance, angular distance alpha. What is this probability? This is a determinant again, where on the off-diagonal coefficients you put alpha. If you calculate this determinant, that would be precisely this value. Exactly the same thing happens for the query, except that we query with some other parameter, query parameter beta. Notice that if you want to balance these two costs, you would rather put alpha equals to beta, at least for the classical version. That's what happens. And the last question that remains is how large the U should be. And the way to analyze this is to ask the following question. I'm giving x3 and x4, and I know that they're short, that they're close to each other because I've chosen enough of them at the beginning. Conditioned on the fact that they are close, how many U's, what is the probability that my U will find them, and my U has the distance between x3 as alpha and x4 is beta. So what is the probability that this distance is alpha and this distance is beta, conditioned on the fact that this distance is what I want, let's say 1/2. It's nothing else but the conditional probability. So this is what I've just said. So the number of centers we need is determined by the inverse probability that I actually find my point, and by find my point, I mean that x3 will be with distance alpha and x4 with distance beta. And you can change alpha and beta in this case. They it doesn't matter which one is alpha and which one is beta. And this is given in particular by this formula. It's a probability taking over random points on a sphere that this happens conditioned on that this is true. Conditional probability, it's a fraction between the probability that everything happens divided by the probability that this happens. Okay. This is nothing else but the Gram matrix of U, of the inner products between U, x3, x4, and the in the Gram matrix for x3 and x4. This is that. So on the mid-diagonals, they are ones because they're all from the sphere. This is an inner product between ux3, inner product between ux4, and inner product between x3, x4. It's a Gram matrix. Now what you do, you plug in C being 1/2, alpha equals beta, and you try to balance the costs with the bucket sizes. If you actually do the math, and it's not very difficult to do, you just so you know all the entries here in the determinant. You just compute this fraction, and this fraction, the inverse of this, so this is the probability, right? And you want the inverse of that. And that will give you the 3/2. And the 3/2, if you put it into the base 2, this is precisely the magic 292. The magical 292 constant.
So here you choose U such that you catch all pairs of points.
Precisely.
Is it clear that this is optimal? Because for sieving you might lose some pairs, and that's also fine.
But you're not allowed to lose more than exponential.
Yeah, true. Okay.
So there's so losing losing pairs would mean that you would have to start with a bit more at the beginning, so to accommodate for your loss. And that would increase this time, because actually the time you need is for each L you do that update. And the longer the L is, then you increase your update, and hence you increase your T query. So we are so the time actually will be the size of L times that, the size of L times that. So this value I've just given by 3 over 2 to the n. And if you could, I don't think that would be an optimal choice to go. So good so far. So yeah, this is asymptotical number of centers. We need to put in our sphere to make sure that with the constant probability, with the probability 1 minus exponentially small, we find all the pairs we need. So we will be losing something, of course, because this is a concentration result. So there are some outliers that will always be there. But by Chernoff bounds, that we can also bound them. Okay, Chernoff bounds may induce another polynomial factors. I'm asymptotical. What can we do quantumly here? It's not that much that we can do quantumly, unfortunately. So for the reason being that we already kind of optimal in the time of finding all relevant centers. It's the time of finding all relevant centers is the same time as many of them we have. The thing we could try to do quantumly, this is what was done in Ty's thesis, and that's what we also extended for a larger case, is to actually go for larger buckets. No, because then once we have a bucket, once we're inside the bucket, we could apply quantum Grover search to actually find the good one. So what we're going to do, so from this picture, the quantum algorithm would do the following. On the query Q, I'm going to find classically all the U's. The reason why I'm not doing it quantumly is because the time is optimal already classically. And I'm going to create the O superposition of these U's. Query all these vectors, x6, x1, x2, x1, x3, x4 in a superposition. That's where we need a QRAM. So it does require QRAM. And I'm going to do Grover search over these two vectors. And the Grover search would be checking whether my Q and these xi's are at the distance that I want. So this is precisely what the quantum version of SIP does. And if you compare it with classical, that would give us, so the update time we do not change. We change the query time. And the query time would be time to get all the relevant centers, classically the same as optimal, and the Grover search inside the relevance, inside each relevant center. So if you want the precise state, that would be as follows. That would correspond to the following state. So first I'm going to make a superposition over all. No, this green is not visible. I'm going to create a superposition over all buckets. Let's say centers which are relevant to my X. I'm going to query all of those, the number of, basically, let's say the size of the bucket. I should put square roots everywhere, by the way. Bucket U. What is the size of the bucket U? Times the X from this bucket. And then I do the Grover search over that. The Grover search will cost me, so this is precisely this. This formulates the number of relevant centers for a given X. This is this quantity. The bucket size, this is this quantity. This is the expected number of solutions. how many times I need to iterate Grover search to get all of them. And actually, you can compute each and every term from this. I've just shown you how to do that. Number of relevant centers would be this value for a beta as a parameter to get for the query point. The bucket sizes will be the probability that for each x we get alpha close. And this is a number of solutions. This is our target distance. Again, you do the optimal choice of the parameters, and that gives us these values, the 265. So yeah, and when people say that maybe the cryptanalytic enters are not that rewarding, this is actually true because we went from 2.9 to 2.265. But that's the state of the art without asymptotical state of the art. You could, what you could do is you could reduce both. You could reduce memory cost first. It doesn't seem plausible with the current techniques to reduce the constants for time. So you could, for instance, what you could do is you could reduce the constant for time, but then it will necessarily incur the cost. Sorry, you could reduce the memory cost, so you could reduce the number of vectors you need to go. So you could reduce the value 2075 to pretty much whatever you want. But then the time will increase. So there is no a priori lower bound on the list sizes. So you could imagine that, okay, maybe we should take some, to get the parameters, we should take some lower bounds on the list sizes, but actually there is no lower bound on the list size. But that will incur time to actually do the search. Okay. What else can we do? As I just shown you, these quantum version of Ceph are actually classical memory Ceph. It does require a lot of memory. You could do, as I said at the beginning, there is another version. There is another way to do SVP, which is called the enumeration algorithm. Enumeration algorithm. It does, essentially what it does, it traverses a big tree. The tree is of size 2 to the n log n, up to a constant. And there's been a work done on improving this algorithms quantumly, which is called so-called backtracking technique. And the backtracking technique is a random walk, is a quantum random walk on a tree. The only thing you have to make sure, well, not the only thing, but one of the things you have to make sure for this particular random walk is you can check whether a vertex of your tree or a path of your tree is a dead end or not. And that you can do by just checking the length of the vector in a subspace. So that's one thing. But on the other thing, you may wonder, okay, if I'm actually low memory, so okay, this was for SVP, right? So I didn't speak about LWSS problem because actually the way we know how to solve it is really via SVP, and it's quantum versus SVP. But then if you don't have enough memory, then it could as well be useful to actually run Grover search just on your search space, and asymptotically, if your vector is binary or sparse, it's unclear to me whether just Grover search over your secret would not be better than the enumeration algorithm. So of course it will depend on how sparse your secret is and how big is log n. So if you really don't want to target SVP but Cis or LW directly, it could be a good idea to actually look what the performance of the Grover search is against quantum enumeration. Another thing I was wondering is whether we could actually speed up another algorithms for LWE, not SVP, but that directly target LWE. One of the other ways to do it is a BKW. So I spoke yesterday to Andres about the potential improvements. So BKW is a two-step algorithm. the first step doesn't seem to be amenable to quantum speedups. That's because the memory is equal to time. But there is a second phase, which is distinguishing phase, where you have to distinguish between uniform and Gaussian with a very small bias. Apparently, there are some ways to do it quantumly faster. So you could maybe play with constants, so asymptotics will not change, but constants may. So, yeah, so I hope the constants will become a little bit more clear. And yeah. So I want to just say that these are asymptotical results. In practice, or if you really want to set up the parameters, you should be careful with what the algorithms hide in big O in small O of 1. But this is also a non-trivial way to actually set those. If you have any questions.
Thanks very much. Great presentation. More questions?
So, in this group research, what kind of oracle do you have access to?
So I assume I have an LWE sample, and I'm going to search for whether my secret is good or not. No, I mean, oracle is just, I'm giving you classical LWE samples. I put a superposition over all my secrets, sparse secrets if I can. And then the checking function will be whether this S is good or not by checking whether basically this version, B minus AS candidate, is short, right? And you know that if my S is wrong, it will be a uniform mod Q. And if my S is the right one, that will be really Gaussian. I can distinguish those.
Any other questions? Well, thanks. And we'll regroup at 11 a.m. for the second half of the morning session. Thanks again.
Okay.